We won't get feedback. All right, I guess we can go ahead and get started. So today I asked Jinning to come in and talk a little bit about the in-house software we built for this. So before I hand it off to Jinning, just talk a little bit about what's out there for commercial power system software and the reason why we developed our own one. First of all, if you look at all the main ones out there, first of all, they're all balance positive sequence. That's generally not a problem on transmission. And for this class, mostly what we're talking about is midterm dynamics. So not the they can do the sub-transients, but they're not usually used for that. It's usually the transient to tens of seconds, right? So that's on the order of a few cycles to 10 to 20 seconds. So I'll talk technically why that matters a little bit. So the controls that are implemented in the standard models and standard software are only local, meaning it's only getting like say for an example, the exciter, right? It's just looking at the terminal voltage, right? And it is possible to get remote signals in some of them, but it's not easy and it's awkward. Okay. Until recently, all they were branch node model, meaning that every substation is just represented by a single node. Okay. So that for most of the time when we're doing these type of studies, like we were doing this class, that doesn't matter. But it does if you want to do anything that's like similar for an operator, right? So the operators need to see the actual substation layouts, which means, the bus breaker model where, what the protection looks like, where the connections are, because you can have a split bus. As soon as you have a split bus, then you've got a different sort of load flow, you've got a different sort of state estimator and so on. No communications model. So that's it there. And most of these are really used for planning or and usually the planning and operations models are kind of different. So they're doing that. Also nothing on dispatch and so on, right? So and when I say no EMS function, that means, there's no inherent state estimator and it's very awkward to use any of the software for doing that. No AGC, okay? So you can't do, AGC is really the only wide area control in most power systems, right? So I think I mentioned earlier, the voltage control that they use in France and Brazil is a wide area control, but that's not done very often. Okay, so part of the reason for all these limitations is historic. They didn't really start doing these studies until I would say the 1970s timeframe. And I believe that EPRI was the first one with their extended ETMSP, which is Extended Transient Midterm Stability Program. And really the underlying technique hasn't really changed in any of these. It's an explicit integration with a fixed time set. So it's not using modern integration techniques. That is a lot simpler to implement and it's more reliable. But if you remember, explicit integration is not numerically stable. So meaning that you're always going to get drift over time. So that's why you don't really use these for beyond about 20 seconds. It's not really a problem. Maybe reliable a little bit longer than that, but you can't just sit there and let the program run for minutes, minutes and minutes of simulation time. There's various approaches to load flow and some other stuff on initialization, but they're fundamentally they're all the same. Okay, so then the basic tools out there, just to if you haven't seen them, are PSSE, which few people are using. We've done the tutorial, so that's fine. That was originally developed or it's still part of PTI, but the person who originally developed that one went to GE and wrote PSLF. So you can imagine they're basically kind of the same thing, right? Underlying techniques are the same. User interface is a little bit better. DSA tools is another one that's quite widely used. That's from PowerTech out in Vancouver, Canada. It's developed originally for BC Hydro. But those two, PSLF and DSA tools, are used less on the East Coast. On the out west, they're used predominantly, more often than PSSE. Power world came in much later, like in the 90s. It was originally just load flow. Its emphasis was on the user interface, but now it has all the things that PSSE and PSLF does. And it's actually much easier to use, I think. But a lot of utilities aren't using it for the dynamics, so they're still using PSSE or Dig Silent is more common in South America and Europe, but it's similar. I haven't really used it at all. ePhaser Sim is another one that's a real-time based. It's not used very widely, but it's meant to be real-time, so it's got some. And then there's a couple of other open source ones. PST, which is developed by Joe Chow at RPI, and then that was slightly modified by Federico Milano, who's now at University College Dublin. But neither of those are supported anymore. Okay, so open source, the problem with open source is it starts off good, but then there's not, unless you really get a big community or you get some sort of economic thing, that they usually kind of fade off and doing that. But they're out there and they can still download them. That's just not supported for them. Okay. For other sorts of phenomena, there's all sorts of other software out there. It depends on what you guys are working on. For faster stuff, the electromagnetic stuff, that's EMTP, not ETMP. Whoops. Because it's electromagnetic transient program, not whoops. So some of you are probably doing more with this type of program, because it does do the transients. And so for the faster phenomena, particularly if you want to do stuff with power electronics, you may need those. Okay, and then there's all sorts of other stuff, whether it's distribution, so it's got three-phase imbalance or short circuit analysis and other supermarket stuff. So there's a lot of other things out there. What Jinning's going to talk about is what we developed in-house, and mostly we developed that around a couple of things that are shortcomings in this. Oops. One was we want to be able to explore the EMS functions, so things like state estimation. We want to use that in controls. We want to do wide area controls. We want to understand the communication model, okay? And we want the market models to be in there. So that's why we did ourselves. And also we wanted to have a lot more, and I could probably say that here too, is these are all pretty limited in terms of how they can do renewable models. They've started adding these to PSSE and PSLF, but they're still fairly limited as far as I know. And if you want to add your own models, it's awkward. Okay. So any questions about that before I hand it off to Jinning? So, oh, and by the way, we have available to us all of these. Okay, so if you wanted to use any of these other, including some of the, including MTP and Map Power. Of course, Map Power is open source and OpenDSS is open source, but I don't know if we have Aspen one-liner anymore, but we have other things through, I think it's SIME, for doing short circuit analysis and that, if any of you are doing that, but not something we covered very detailed here. So, yeah.
Quick question. So I know you mentioned that in planning, you might just use like the bus node model, and in operations, you want a more detailed model. What's that one called?
So it's the bus breaker model.
And so what's the detail?
So you get the substation layout, right? So in a substation, you have what's a standard substation it's got several feeders coming out of it, right? So you've got then you get the layout of the transformers that are on that, and then also the bus protection. So it's usually something it's called breaker and a half, which just is one of the types of protection things. So it kind of tells you also where on the bus bar the breakers are located, and also the transformers. So you need that if you're in the operator, okay, for and operating the system, you need to know that detail, because when you're taking action as an operator, most of the time, what it is switching things in and out. So you've got to know what the layout is at substation, right? So if you want to, if you go back, now PSSE does have that bus breaker model, although most of the time people aren't using it. But what people did instead was they created something called the operator training simulator. So for training operators, so they get used to how to work with the EMS and open and close switches and restore things and stuff like that. They use something called the operator training simulator, but that had as a model, you can call it it's a pseudo dynamic model. So none of the generator dynamics that we've been studying in here, it's sufficient for doing AGC, and it's sufficient for doing restoration. But in the numerical integration routines and all that stuff, what it is it's a load flow with a frequency that can vary somewhat. Okay, based on the balance of that. So you could call it, so it's pseudo dynamics. Everything is done as snapshots of algebraic equations, load flows with some people call it a governor load flow, because you allow there to be different frequencies. But anyway, so that bus breaker model is mostly for the operators. However, if let's say if you're trying to do some other functions for controls, or you're looking at state estimation, you kind of need that as well, because if some of those breakers are open, then it changes the topology and stuff like that. So
Okay, gotcha.
okay. Anybody else? Okay, Jinning, I'll stop the share and turn it over to you.
So, can my voice convey to the audience? Oh, okay, great.
You should be able to hear it.
Sure.
If people online, if you can't hear, let us know.
Morning, everyone. I'm Jinning, and I'm glad to be invited here to give a talk about our recent progress of the current large-scale test bed, short as LTB, in this presentation. So the title would be Advancing a Decarbonized Power Grid, a transient stability perspective with the current LTB. So what is LTB? First, LTB is a closed-loop platform for rapid power system prototyping and testing. The closed loop here means your controller are in the loop of the power grid. Your controller will take the signal from the power grid, and then the control signal will be fed back to the power grid. And second, we want to have a comprehensive functionality platform. It means we need to do dynamic simulation. We also need to do dispatch simulation, and we can have a geo-visualization for the control center. Here, I want to say that the dispatch part of work is an ongoing project. And then for now, we have 4 core modules. First, Andes is the dynamic simulation engine. In Andes, Dr. Han Daocui proposed a hybrid symbolic numeric framework for easier modeling and rapid numerical simulation. And the second one, the AMS. AMS is the dynamic information interface dispatch modeling and simulation. I am working on this right now. This is still an ongoing project. Third is the AGVIS. AGVIS is a geographical visualization for the energy system. So with AGVIS, you can visualize your power system simulation results in a geographical map. This can give you an illustrative understanding to the power system status. And the last is the DIME. DIME is the data messaging environment for these multiple power system components. And then there is an interesting question, why LTB? I mean, we already have many simulation tools, not only commercials, but also open source ones. Why would we still need another one? Here are some motivations. First, a flexible structure means that you can use each component of them, but at the same time, you can also use them together. We call it federal use. to give you a comprehensive analysis. And second, as a open source platform, it is totally transparent and customizable. You have access to the every source code if necessary, and you can change the code itself. You can have new numerical integration method, or you can have new models. Third one is the interoperability. With this platform, you can easily to develop the code simulation with dispatch, with distribution, or any other energy systems. Then we aim to lower the learning cost for the user. We design the consistent style across the APIs and documentations for each modules. And the last, we have a prosperous community to give the continuous development work, and we have an active online discussion. If you are interested, here are some links. I put the QR code here. If you are interested, you can give a quick scan. And then I'd like to show an example for federal use. We can use LTB for a dynamic contingency analysis. So on the left side, the three modules are running in the backend, and on the right side, we are seeing the LTB aggregates to give you the geo-visualization. And in this case, we are using the reduced ERCOT 2076 bus system case, and there is a generator tripping event at the 1 second. And this is the aggregate visualization screenshot. On the left side, we are showing the bus frequency, and on the right side, we are showing the bus angle. Let's see the simulation. So now we can see that the system frequency is experiencing a frequency drop. And also on the right side, we can see the bus angle is also under normal value. But now the frequency has been increased again. And the bus angle is also increased. And now we can see that both the system frequency and the bus angles are over the normal value. Here I selected part of the simulation. And then let's go back to the.
Just make one comment. So, and one of the reasons we developed this is because, like, when you're doing larger studies, right, it's often hard to find out what buses you need to look at. So the idea is, if you see this, like if you're looking for oscillations, then it's very easy to see what's oscillating against what. So that's convenient.
Yes.
Yes.
Hey, Jinning, this is Hoy. So I have a comment here. So not sure if we can put a color bar in this slide or in your visualization web page, so that color bar can show us the frequency value and the angle value for the different colors, because even we know maybe the red color is for the lower value. And the green or blue color are the normal value, but I think maybe a kind of color bar is better. Yeah, that's a suggestion. Yeah, but you may decide if it's useful or not. Thank you.
Yeah. I also realized this issue that we have put this feature in schedule to give a legend bar on the visualization screen, and so then the user can have a intuitive understanding of the animation itself. For now, the user can define the color range, but we don't have a color bar plotted out yet. But this will be a feature to develop in the future. Thanks.
Thank you, Jinning.
Okay, then I'll continue. So here I grabbed some screen snapshots from the aggregates. On the top line, the bus frequency, and on the bottom line, the bus angle. And we can see that the frequency is dropped first and then increased. And similarly, the bus angle also dropped first, but then increased. And then we can dive into the ends to have more detailed analysis. So in these figures, I plotted out the generator frequency and voltage on the top two figures. And then in the lower two figures, I plotted out the generator bus angle and the load bus angle. So we can clearly see that the system frequency is dropped first, but then the system frequency over the 60 Hertz. Given the lower two figures, we can find out that the bus angle are so different between the slack bus and the other bus. This means that the system might already lost the synchronization. This is a demo for the LTB failure use. And then I'll go to the Andes part to give more detail of this dynamic simulator. So in the Andes, we have the conventional analysis routines such as power flow, eigenvalue analysis, and time domain simulation. And in the Andes, we enabled the rapid modeling with this hybrid symbolic numeric framework. And we already have a comprehensive model library. In this library, you have all the common use synchronous generator model, the excited model, or the turbine gun model. You can also use the renewable models. I'll talk about the renewable models later on. And with this LTB Andes, what you can do is that other software may not be easily used. So first, Andes is a fully open source software. We have the active development and support from the research community. So here it is mainly contributed by Dr. Handel Cui. He is still actively do the development work to Andes. And the second, we designed a user-friendly API. So with this API, you can do the screening use and integration with other tools. Third is that we have a ranking list. It shows that Andes has been the most popular open source dynamic simulator. In the last one, interoperability. This means you can use Andes to integrate with other simulation tools. For now, we have implemented the AGC function, the transmission distribution co-simulation, and the RTED TDS co-simulation as an example for dispatch dynamic co-simulation.
So this may not really be familiar with the RTDS stuff. So that's real-time digital simulator. So that's a hardware-based thing. So Andes can sync with that, and then and that's also three phase.
I may didn't explain this clearly. So for the RTED TDS co-simulation, I mean that RTED stands for the real-time economic dispatch.
You're talking about the other thing. Okay.
Yes, it does not mean the EMT simulator. RTED here means the real-time economic dispatch. It is the instance of the dispatch formulation or the extended OPI formulation. So
but we can do these RTDS as well.
Yes,
yeah.
yes.
Okay, but you meant your real-time dispatch. Okay, sorry.
Yes. To further complete the Dr. Tomsovic's comment that this year we have a project at CURENT to integrate the hardware testbed and the large-scale testbed. That function is similar to the hardware in loop simulation enabled by RTDS, but we have different focus. That is also an ongoing project. And then let's see a detailed case of Andes. We will do the transient stability assessment with renewable penetrations. So in this case, we are using the HVE14 bus system. This is a building case in Andes. So case one, we are using the power grid with synchronous generators, and in the comparison case, we replaced one synchronous generator with wind turbine. You can find these two cases from the Andes library. And so in this case study, the contingency is that there is a synchronous generator tripping at 1 second. And for the dynamic models in these two cases, there is a table. So in case one, we have the synchronous generator model, general, we have the turbine governor model, and we have the exciter model. In comparison, in case two, we replaced one synchronous generator with the wind turbine. We have the renewable generation model, REGCA1. We have the renewable governor model, WTD, TA1. This is for a wind power model. And we have the renewable exciter model, RECA1. And then we have the renewable pitch model, renewable power plant model, and the renewable aerodynamic model. So here are some tips that first, all these models are, you can find them in the ANDIS documentation. We have an online documentation for ANDIS. And second, although we didn't use this time, but we also have reforming converters, REGCV1, REGCV2, and REGCF1 to F3. And the third is that this time we are using the plant level model, but we also implemented the distributed generation and protection model. PVD1 is for the distributed power, solar power generation, and ESD1 is the distributed energy storage model. The DGPRCT1 and the DGPRCT-EXT model are used for the protection study. And the last, if you want to know more about the model diagram, you can search the model name with PowerWord or ESIG. These two softwares provide the model diagrams online.
So let me just, so basically Genro is like what we've been studying for the general ones, but there's like, the main ones are Gen classical. So
Yes.
you can have a classical model, or the Genro, which is a two-axis model we've been studying. So these are, I don't know when they started using these names because they're not very descriptive, but I think it was PSSE started using them. Basically, everybody follows them, and they're now kind of IEEE standards. And then the exciters, those are again IEEE names, but basically it's what we were studying. Well, we kind of did it a little bit simpler for things, right? We didn't really do the governor stuff, but that's okay. Anyway, so these are the names are confusing, but they're exactly what you've been studying. So.
Yes. But once again, you can search all these models online, not only in ANDIS documentation, but also many other sources. And then let's do the simulation. This is the time domain simulation resource. So on the top two figures, I plotted the statewide frequency on the top left and the slack bus voltage on the top right. And on the lower one, I plotted the slack generator excitation voltage on the lower left and the bus angle on the lower right. So on the lower right, the y-axis, this bus is the bus connected to the generator that was replaced with the wind turbine. So in these figures, we can see that there are more transient pressure to the system when we have wind power generation in the system. We have the lower frequency nadir, we have more bus voltage dispersion. And also in the lower right one, you can see that the bus angle is increased much faster than the original system. So another perspective that we can do the eigenvalue analysis for small signal stability analysis. In this figure, it shows that the impacts for small signal stability is complex. Some points are getting away from the right half plane, but some points are getting closer. This means there is a complex impacts on the small signal stability. This can be caused by many reasons because you can have different renewable control models. You can have different renewable power plant controls. You can have different wind turbine models. This might be worth for a further investigation. that's all this time, and we have many users and partners for now, and we are still working on this project. Welcome any question or comments if you have.
Can you go online and show like some of
Yes.
the models and stuff?
So here we have some online resources. So first we have a website to give the overview of the large-scale test bed. This website is still in progress, and we updated this website regularly. And then this is the Andes code repository, and we can see that there has been a significant download members of the current LTB of the LTB Andes. And so here is the Andes documentation. In this documentation, Dr. Handelsway discussed in detail how he developed this software and all the developer level detail. And most useful it might be the model library. In this model library, you can have all the implemented models in Andes. For example, if you want to investigate the renewable, you can go to here. The renewable generator group, we have such many models. You can use each of them as long as you need. And in the model library, we listed out the parameters, the variables, and the initialization equations. The only drawback for now is that we don't have a model diagram in the Andes documentation for now, but a alternative way would be that you can search most of them online. For example, the REPC the model REPC-A1 is the common used plant level renewable model, and this one is also implemented by PowerWorld and many other softwares. So you can find the model diagram here. So for most of the commercial grade model, we are follow the same structure of the commercial softwares. There are also some models that Dr. Handels implemented them by himself. For example, if you want to do the grid forming converter study, we have the RGC V1, V2, and the F1 to F3. The RGC F1 to F3 models are developed from a APRI meeting notes. The APRI summarized some generic grid forming converter models. You can also find them online. But in case if you have any question that you can put them to the discussion board, and there are many active users, they might help you somewhere.
Let me just say a few words, because we didn't really discuss, had a chance to discuss much on the modeling thing. So when Jinning's talking about grid forming, it's in contrast with grid following. So up until recently, most renewables were connected through inverters where it's grid following because they don't do anything about the frequency. They can control the voltage, but frequency is what it is. It just stays synchronized with the grid. So, but you have to have something that supplies the a frequency reference, right? But in a larger grid, if you've got other spinning resources like synchronous generators, you've got that frequency reference. Okay. Now, well, you can't have a situation where everything is inverter based, right? So then you need at least one that's providing that thing. But grid forming is generally, now people are trying to put lots of them together so that they can provide they have the capability of providing a frequency signal. Although usually you have to have some sort of a leader follower type of thing, so you're not fighting each other. The most important thing though, out of all that, whether it's grid forming or grid following these renewables, is these are not detailed models of the power electronics. So it's nothing about the switching, nothing about how it's actually generating the signal. It's only about the things that we care about on the grid, which is voltage controls, real and reactive power outputs, the frequency, frequency control. So you can do artificial inertia, right? So you can do lots of different functions, but the way we're going to model them on this stuff is none of the detailed inner loops on the power electronics, right? Because those are too fast. So it's just the outer control loops. Okay. So the models can be, they look pretty complex there, but just think of it in terms of certain functionality one. The other thing that matters much more now than with the traditional generators is we talked a little bit about limits, like on the exciter, although I didn't really get details of models because it's analysis gets harder, but it's in our simulators. But so for traditional generator, I've got the exciter model with a hard limit due to the current limits. But there's actually quite a bit of room in there. So you don't go into those hard limits very, very easy. Like if you looked at what Jinning just pulled up, you saw several blocks that had limits on them. Okay, those limits are a lot tighter for power electronics. So you're very easy. Yes, you look at these, say Qmax and Pmax and that. These are going to be tighter, and that's going to make a difference in your simulations. Because, and the reason they're tighter is because, if I look at a traditional generator, what I have is this huge magnetic field and these windings and stuff, and it can easily produce very high levels of current when you have a fault or something like that, or some sort of change. These all have to go through the electronics. So any current output is going through those things, and they're going to be, those have to be hard limited, otherwise you're going to burn up the devices. Okay, so it makes those limits are kind of fundamental to understanding what's going on. But even, I know this looks kind of complicated, but it's got the filters and stuff like that, but none of the switching is in there. This is based off of what are called averaging models. All right, so you don't have to know a lot about power electronics to kind of to sort of use these and understand them, but those are the things, knowing that you can control P and Q, knowing you can do something for frequency, knowing that you can do something on voltage references, and then your controls, you should be fine. And then the hard limits. Okay. So
Yeah.
you go, Jinning.
Here I have a further comment to further clarify this model. This is the renewable power generation model, but different from the EMP simulation. Here we simplified the model for the transmission level power grid simulation. The very first motivation we are using the physical simulation that we cannot do the EMP simulation in such large scale. So here we do some model simplification. So you don't have to do the switching behavior in this model. You can treat it as a conventional generator or something. So here we made the simplification, and there are many other models. They follow the same philosophy to do the simplification. This is a way before we can do the full-scale EMP simulation. We are using this way to do the renewable penetration study in the transmission grid.
Go ahead.
I just it's a bit different from what we're discussing. But two questions for Andy's. You guys have a way of automating, automate several simulations. Is there a way to automate things using Andy's? Like a PSS it is like Python automation. So like run several, run like 20 dynamic simulations or different kind of things.
Yeah, this is a good question. That actually this is the, personally speaking, I would say this is the biggest advantage than the PSSE Python API, because Dr. Han developed this tool with a carefully designed user API, and it is primarily used for the streaming use. So you see there is a example section in the documentation, and you can use it by code. And a much better advantage is that once you finish this simulation, and after maybe one year or 2 years, you can still open the code and run it again. So you don't have to do it by, you don't have to do it manually. You can have all the things recorded in the code.
Just because they're not, so now, so it's written all in Python. Andy's is written completely in Python. All these routines are written in Python. So that means the scripting part is pretty easy. I mean, it's built, he's got the scripting thing built in, but it works. Yeah. Right. And so then, and you can run it on any platform that you can run Python on.
Yeah, and this is originally developed fully in Python, so it would have the benefits from all the Python advantages. It has the similar API style. It has the integration capability with many other Python libraries. For example, Dr. Hanlos also developed just a quick information that there is a reinforcement learning library developed by Dr. Hanlos that you can do the reinforcement learning study with Andes as a simulation environment. And another quick comment is that as far as I know, Dr. Hanlos is focusing on the high performance computing right now, and he might give a substantial improvements to the simulation core of Andes in the future. That is another attractive part for Andes. It means that you can take advantage of the modernized computation hardware architecture. This is a thing that not discussed publicly previously, because PSSC has been developed for many years, but when back to the time we developed PSSC initially, we did not have such modernized computation hardware. But after many years, we have many advanced computation hardware. We have new CPU architectures, we have GPU hardware, and they might help us to do the power system simulation in a faster manner. Dr. Hanlos also has some studies focused on this. If you are interested, you can do a Google search.
Yeah, so the other thing about Andes is it's not, okay, it can take advantage, although we haven't pushed that too much with the high performance computing, but it can take advantage of, multi-core structures and stuff like that better than the commercial software. So it's actually faster, but it's also more robust numerically. So if you want to do longer stable, so because it uses implicit integration, unlike any other commercial software. So it can do variable time step is also needed. When you're doing real time, you don't really do that, but you can do the, well, one of the reasons you want variable time step is when you have a disturbance, you get a shorter time step and your integration is more focused, right? But then as things die out, you don't need to do, things aren't changing as much, you can get a longer time step. So you're going to be much faster there, but also it's numerically stable. So it can, with implicit integration, I don't know, we've really done this, but it should be able to run for hours without diverging. So
yes, there is also a part in the documentation that give you more detail how the DAE computation is done in Andes. And a difference is that in Andes we are doing the DE and AE simultaneously. We are solving them together, but PSSC is doing the DE and AE alternatively. So in this DAE, in this manner in Andes, you can have a longer time stamp and you can have a better numerical stability.
So what he's talking about is what we did in class, right? What I described is what is done in PSSE and PSLF, where you're going back and forth between the dynamic equations and the algebraic equations, right? So that that's more limited. By combining them, you can be by solving them together, you can be faster. So, but anyway, but what I described in class is what, as far as I know, all commercial software does. So going back, can we? Let's go. Would probably be interest in terms of the models because we do. Do you have a type 3 DFIG model you can pull up?
I'm not sure which one is the DFIG model, but
let's see what you have for wind turbine.
Are you referring maybe this model, the renewable aerodynamics?
Okay, so this one's got some of the this has got the variable pitch and everything in it.
Okay, we also got the I got in mind the renewable government. We might don't have the DFIG model right now. We have some alternative models for the wind penetration.
Okay. What do you have for a solar plant?
Yeah, solar plant, you can directly use the REGC-A1 and REGC-P1. REGC-A1 is for the generic renewable power plant, and if you add some wind turbine control, it can be a wind power generation, but without that, you can still use it as a solar power generation. This names can be confusing at the first glance, but you can do a Google search to see what they are doing.
And these are standard names. So it uses the same data format. It's got its own data format, but it can import the ones from. So if you've got PSSE file, which has got a bunch of these models in it, it can import them.
Yes, there is also a interesting part that you can do a conversion from the PSA file to ANDIS file in case you want to experience ANDIS file yourself. You can easily do the file conversion, and then you can have all your files transferred from PSA to ANDIS. And then you can edit the IO files in ANDIS. Any other that might be helpful for them?
I'm sorry.
I mean, any other materials that might be helpful for the students?
Yeah, I'm trying to. So, yeah, this all depends on what your research is related to. But I think if there's clearly going to be a little bit more of a learning curve with this one than with PSSE or with say PowerWorld. PowerWorld's probably the easiest to use. But if you need to do a lot of different things with renewables and renewable controls, it's worth the time spent learning how to use it, because in the end it'll be much easier to do. Oh,
yeah, here we already have some research enabled by the LTB support. So here is the disturbance propagation study using ANDIS to do the simulation. And in this study, we investigated how the electromechanical wave is propagated in the power grid. And there is the transmission and distribution co-simulation framework for frequency study that we are using the ANDIS for the dynamic simulator, and we are using the OpenDSS for the distribution network. This is the example how you can use ANDIS with other simulator tools.
yeah, I probably have to spend a little bit on that. So when Jinning talks about the electromechanical wave, and some of you have worked with Dr. Liu, so you've seen like the FNet stuff, right? So you see like when a disturbance starts somewhere in the grid, right? It propagates through the grid, but it doesn't propagate at the speed of light, right? That's an electromagnetic transient. It propagates what people are calling electromechanical wave. It's basically from the inertia of the generators. It's going to take a while for that to move across, and it varies on the loading, depending on what the inertia you have in the system, what the disturbance is, but it moves at anywhere from a few hundred miles per second to maybe 800-900 miles per second across the system. But it kind of looks like a wave. In fact, this was first discovered on the West Coast by, well, I don't know if somebody before John Howard, but anyway, one of the engineers at BPA discovered this because you could see things move across, but it moves across slowly enough that you can sort of respond to it. What this study, what Jinning's talking about, is this study looked at when I start having inverter-based resources, how does that affect the propagation? It has an effect because no longer I'm replacing rotating machines with something without inertia, although I may emulate inertia, but let's say we're not emulating inertia. Then what's going to tend to happen is that wave tends to speed up. Okay, so it also changes a little bit in terms of how the ring moves. But Jinning's point mainly is that we're able to do this type of simulation in ANDIS.
Yeah, so here I want to show that with ANDIS you can have the potential to easily integrate with other tools. You can do the flexible dispatch model. You can have your renewables in the dispatch state to participate in the energy market or the ancillary service market, and then you want to verify this with a detailed dynamic simulation to verify the dynamic performance, such as the dynamic security or the frequency regulation matrices. So if you are interested in the frequency study, this TNT co-simulation framework might be good reference. And back to the NDs, we have a poster to show the hybrid symbolic numeric framework, how this framework will enable you to do the easier modeling work and also give you the ability to do a fast numerical integration. You can have more details with the website's documentations if you are interested.
Yeah, question. On the YouTube page for this, you guys have like the tutorial, it's like a basic tutorial for new users.
Yes.
Oh, okay, which one?
Yes, so for the new users here, you can we have a tutorial section that tell you how to use NDs, neither from command line user or from the
Yeah, like video tutorial. YouTube.
so
Like,
yeah,
make it easier for people and easier videos.
we have a YouTube channel, but for now we don't have tutorial videos for NDs for now, but those videos are also in plan. We can do that in the future. For now, we have videos for the LTB demos and the edits, the visualizer. We have a video tutorial for the visualizer. In that video, we can teach you how to visualize your dynamic results in the geographical map. And we have some demonstration videos for the current LTB. But to be honest, we don't have video tutorial for
Yeah,
us now.
like future to easier, available, how to run powerful.
Yes. Yes.
So people learn easier with videos.
Yes,
than going through like documentations.
Yes.
Like, it's easier to then go to the documentation after watching maybe a series of.
Yeah, that's a good suggestion. We should be able to do that because, well, we've done, Huntao, who's the main developer here, it's done, talks on level. He's done them with me, trying to teach me how to use it and stuff like that. So what we can just sit down sometime and record one of those and post. That's a good suggestion.
Yeah.
Well, there's a difference between doing it. There's an easy way to do it, and we want to do a really good job. It probably takes a little more effort to go through them, but it should be easy for us to just record one of our training sessions.
Yeah, before that, there is the alternative resource that might be helpful. That we have a course project that are using NDs for the transient study. We haven't used it. We haven't used this this time, but it is public, and you can take a look for. It can help you how to use NDs for your research. It can be a good ramping up material.
Yeah, so this is what originally the project that I wanted to use, but then as I went through it with Jinning and Huntao, I thought it was too hard to use in terms of too much, not too hard to use, but just too time consuming. Like by the time we'd have to spend a few weeks, I think, before you get used to using new things. But you're welcome to go on there and use, actually you're still welcome to use it for this class if you wanted to, but I think most people are using PSSE on their project, but anyway, it was doing more or less the same thing. It's got, I don't know which did that one use the WEC model or did that use the MPCC?
You mean this project?
Yeah, what you were just on.
This project, we are using the NDs to do the. So in the,
what was the system model though?
The system model, it depends on the test case you are using.
Okay, so it was
Yes.
any test case was fine. Okay.
Yeah. So this course project is designed to help new users get familiar with NDs first, and then you can do a simple critical clearing time study with NDs. And regarding the let me show you the case file. So there has been some existing test case in NDs, and you can directly grab them to use. So for now, we have many model verification case on the IEEE 14 bus system. And also we have the IEEE 39 bus system with dynamic models. And also at current we developed the MPCC system and the back system. In these two systems, we also have the dynamic models in there. You can do the dynamic simulation with this test system. And
MPCC is like the New England area, in New York area. So it's an older model. It's a reduced
Yeah.
model, of course, but
regarding this, you can we have a map to show you what's the system. So here, let's go to the Agvis documentation, and we have a section for the. Yeah, this will give you a. So for now, this is the 39 bus system visualized by the Agvis, and this is the WAC system to the west part of the America. And this is for topology, and this is the screenshots for dynamic simulation. And then this is the MPCC system in the northeast area. And also we have a reduced ERCOT system. And we also have a EI connection. This one is developed by the current, I think. And also some other researchers contributed the text synthetic to sound bus system with dynamic models. This one is the dynamic part is not verified by industry material, but you can still use it to verify the performance for Andes.
so the synthetic models were based off of a DOE project that Tom Overby, who's now at Texas A&M, had, and that DOE project was mainly so that researchers could have open access to realistic models, because rather than having to sign NDAs all the time on these things, and then share results, right? Because normally when we work with the utility, right, we can't share the data that we have because it's considered sensitive. So what they did was they, based on statistics of different grids and how they developed several synthetic ones, and then scaled them up and tested. And then these are open source. There's some smaller ones. I think there's some bigger ones too, but they're free, freely open to download in standard formats from the Texas A&M website. But this 2,000 buses, at least that's starting to get decent size for doing large scale studies. Yeah.
And then we have a synthetic North American power grid for the topology. This is the geographic map for the North American system. This is for research purpose only. This is not for any realistic power grid topology. And to my understanding, we have part of the dynamic model in this system, but this system is not used that active in research. That's all the existing case in LTB. And
Question?
Yeah.
So what's the advantage or significance of the actual test bed versus just doing simulations with the models in the model library? That's the using the hardware test bed. What's the
The hardware test bed.
yeah? What's the
So the hardware test bed is, if you've seen it back there, right? It's an actual three-phase system, right? And it's a more faithful model in the sense that it's a real system, right? So it's not ignoring the faster transients and stuff like that. It's got all the switching in and stuff like that. So it should be that you're more able to carefully validate something. So you know, on our models in the transmission system, and that not only is it we're only doing balanced systems, but we're also simplifying lots of things. So there's certain fast phenomena that we wouldn't see, right? With the hardware, it's the actual hardware that has to work together. You will see those, and it's got real communication systems. It's got real measurements. It's got real protection. So then all those things are integrated in. So it gives you a certain amount of fidelity. There's clearly certain phenomena that you won't be able to see in something like this, like inverters. if they're weakly connected to a grid, they tend to have something called you've heard of it before, resonance phenomena. Essentially, they'll be resonating against the system. You cannot see that if you use the types of models that are in Andes and the LTB. You have to have some actual hardware to see it. So, no. Other questions?
Yeah, this is Howie. Hi, Jinning. Thank you for the introduction about the Andes. Yeah, it's very interesting. So I have one question about the efficiency of the current version Andes. So I'm wondering if compared to PSSE, how about the efficiency now? So for example, if we run a system to the same system in PSSE and Andes, so will the Andes be faster right now?
Hello, Howie. This is a good question that for now we don't have a quantified results to benchmark Andes with PSSE or any other commercial softwares. But this is also a scheduled work. We want to have a leaderboard to benchmark those popular simulation tools to compare their performance. For now, I only have experience that and for the simulation speed, and it is better than PSSE, but I don't have any quantified results to prove this for now.
Okay, thank you.
So you
Go ahead.
just noticed that it tends to be faster, but you just haven't actually done careful comparisons. Okay.
Yeah, there is not a careful comparison yet, but I might have some preliminary comparison later on, and I'll put them online if I got some.
Comments? Yeah, but since you guys obviously tested it on standard IEEE cases, we're already sure of the accuracy of the software, at least based on standard IEEE models. So
Yeah, in terms of accuracy, we have benchmarked it against the standard model. So you get the results are consistent with PSSE and Power World and that.
Yeah, for the verification part, there are some online materials to show the accuracy of Andes. This is also in the documentation. If you are interested in, you can take a detailed look in.
Yeah, I was making a comments to how it should know talking about.
Yes.
Yeah, so the accuracy we haven't done significant on speed. It does on speed, yeah.
Yeah. Hello, guys.
Hey.
Yeah. Hello, Johnny. So just I want to contribute about this one. How a question about the comparing between the PSSE and Andes. So I just tried with my research about the comparing result. So there is no difference between those results.
Okay.
To my understanding, the difference, although you have the exactly input system file, and
this is like just work faster on the PSSE. Yeah, that's it.
Yeah, this question that to my understanding that even given your exactly same input file and models in the case, you might have any difference in the results from any other software. This is because when implemented the model, different softwares might have different technical details. You might have a different limiter design. You might have a different limiter simplification or something like that. But in Andes, you can have access to the model detail, how you implemented the model, every part from the input to the output, from the governor to the exciter. But in commercial software, they give you the manual, they give you the control diagram, but you don't have access to the things behind the user manual. That's the advantage. That's one advantage of open source software.
So the follow up that if you're interested in the difference between the sort of commercial software, there's a report. I think there's a paper in IEEE too on this that was comparing PSLF, PSSE, and PowerWorld, the three commercial ones, and there were discrepancies between them just because of the way they implement things. I think usually it's a few particular things. It's something like 3 terminal things they do a little bit differently. Then they bury a few heuristics in the code. One of them has to do with when you do line faults or any sort of fault to the system. If the voltage dropped below a certain level, the load model has to change because you can't use constant power. So typically they like below 0.7, they just turn the load into an impedance, right? But it's not clear that each of the software does it in the same way, right? There's it's buried inside the code for some sort of trick. I don't even think you can change what that is. Okay, so the reason, for that one, the reason you have to do that, right? If it's a constant power load, once the voltage drops too low, then the currents are going to be too high. It's just, you're going to have convergence problems, and it's not realistic either, right? It's like if I've got a very low voltage, my load is no longer constant power, right? It's not going to just keep drawing more current. So, but those are not explicitly modeled, those types of things, right? Okay. Other questions? All right. Okay, so thanks, Jeannie. For the rest of the class, 522 students that are online and here. So we got 2 lectures left. What I plan to do is, based on our discussion earlier, we said a little bit of reliability. So I'm going to talk about reliability and resilience. Okay, since that's the newest sort of interest. So again, we won't have time to do any homework on it, but I'll do some basics on reliability and then the difference between reliability and resilience. We'll do that starting Thursday. Okay, and Jinning, thanks. Appreciate you coming and help us out.
Thank you.